Hello, in this chapter we will find the inverse of a matrix. Okay, let's get started with the definition. So if you have a matrix A whose order is n, that means I have a square matrix A whose order is n, then for the inverse of A we will say that there is another matrix B, and that B is called the inverse of A if that B satisfies these two properties. The first one is A times B is identity of order n, and B times A is also identity of order n. If these two properties satisfy, then we say that B is the inverse of A. So given matrix was A, and this B is called the inverse of A if B satisfies these two properties. I mean, if you multiply B with A from the right side, or you multiply B with A from the left side, you will always end up with the identity of order n. This is the definition of inverse of a matrix. Let's do an example. So in this example, I have a matrix A and a matrix B. So we have to verify that this B is the inverse of this matrix. So how to prove that this B is the inverse of A? So by the definition, I will look at the definition. In the definition, my B is the inverse of A if whenever I multiply B with A or A with B, I will always end up with the identity. Since these two matrices are of the same order, their order is 2 by 2, when I will multiply these two matrices, either A times B or B times A, I should end up with the identity of order 2, because both matrices are of order 2. So let's do multiply. First I will multiply A with B, then I will multiply B. So let's first calculate A times B, then we will calculate B times A. So after calculation, I will get this value, and then after simplification, you will check this is identity of order 2. So that means when I multiply A with B, I will end up with identity of order 2. Now I will do another multiplication, but with the reverse order, B times A. And I will expect again to get the identity of order 2. So I multiply B with A. So I have interchanged their value. First I have written down B, then A. When I multiply and do calculations, I will get this value. These calculations, if I simplify them, I will end up with the identity of order 2 again. So you have checked that when I multiply A with B, then I get identity of order 2. If I multiply B with A, then again I am getting the identity of order 2. This means that these two matrices are the inverses of each other. Hence, this is proved. So next, we will talk about the uniqueness of the inverse of a matrix. Let's write the statement, then I will explain. So the statement is, if a matrix has an inverse, then that inverse is unique. So let's assume that this is the space of all matrices. All matrices. Suppose there are a lot of matrices here, and suppose this is a matrix, this is a matrix, this is a matrix, this is a matrix. There are names, for example, this is A, this is B, this is C, D, up to so on, blah blah blah. These are all matrices. Out of these matrices, some of the matrices will have their inverse and some of them will have no inverse. For those matrices who have inverse are special one. For example, if A has inverse, suppose that B is the inverse of A. I mean, if A times B is identity and similarly B times A is identity, and if B satisfies this property with A, with respect to A, then there is no other matrix which will satisfy the same property with A. So the matrices, if they are the inverses of each other, they come out like twins, as you have mentioned in the lecture. So this means that if a matrix has inverse, then its inverse must be unique. There is no other matrix which will satisfy this property. Okay, so we have to prove this statement. Since this in this statement we have to prove the uniqueness of the inverse of a matrix, so we assume that that this statement is false because we want to prove it. So on contrary, we assume that this statement is false. When in mathematics we have to prove something, we usually assume on contrary that this is false, and then if there comes a contradiction, that contradiction will imply that the statement of our assumption was wrong, so the original statement is true. So we will assume on contrary that A has more inverses. What we have to prove? We have to prove that A has only one inverse, but we assume that no, this statement is false because we want to prove that it is true. We assume that it is false, then we find a contradiction. So we are assuming that this statement is false. This statement is false means A has more inverses. It is not unique. We are assuming that the inverse of A is not unique. That means there are two different inverses of A. This implies B is not equal to C. So we are assuming contrarily, we are assuming that this statement is false. Okay, we have assumed that there is a matrix A whose inverse is not unique, which is totally opposite of this statement. So if the inverse of A is B, then that means A times B is identity and B times A is again identity. Okay? Similarly, if the inverse of inverse of A is C, that means again if we apply the definition for the inverse of for these two, I will get A times C is identity. Similarly, C times A is again identity. So these things we have assumed. So we will proceed this theorem and we will assume these things are true. Okay, because we have assumed these things on contrarily. We have assumed these things. We have assumed these things that A has two inverses contrarily. We have assumed contrarily and we have explained it here. Now our aim is to find a contradiction. Let's find a contradiction. Okay, we are given that A, B and C are different. Let's find B. What is B here? You know, I can write B is equal to B times identity. Okay, and from here this identity is equal to A times C. So I can write either A times C or C times A. So I'm writing this identity equals to A times C. So in place of identity, I'm writing A times C here. Then I will use the the associative property of matrices B times C. Okay, this is called the identity property. Identity property, and this property, this is since C is the inverse of A, therefore I have written this thing instead of identity. So inverse, C is the inverse of A, and here I have assumed the matrix multiplication associative property with respect to multiplication. Associative property with respect to multiplication. And then what is B times A? You can check that B times A is identity here. So I will write here identity times C. And now if I multiply identity matrix with any matrix, I get the same matrix. Here I have used the identity property. Identity property. And what property is used here? Because B is the inverse of A, therefore B times A is identity. So here I will write B is the inverse of A. So the left hand side is B, the right hand side is C. This means B is equal to C, and which is a contradiction. How it is a contradiction? Because our assumption was that B and C are different. But here we got that B and C are same. So both statements cannot be true at the same time. Either this is true or this is true. So both cannot be true at the same time. This is called the contradiction. A contradiction is the statement which is always false. That means this is always false, that B and C are different as well as B and C are same. This is always false because only one statement can be true, both cannot be true at the same time. So this is the contradiction, and this contradiction only arose because we assumed that A has two inverses. And from this data, I collected this data and I used this data here to find a contradiction. So this data is because of this data, because of this assumption. So when a contradiction arises because of some assumption, that means that assumption is wrong, which means our contrary assumption is wrong. What does that mean? Our contrary assumption was that A has two inverses. That means this assumption is wrong, hence A has only one inverse. This contradiction implies A has only one inverse. A has unique inverse, in other words. Hence, the theorem is proved, which is the claim of the theorem that if a matrix has an inverse, then it is unique. So look at an example. In this example, we have to show that, or we have to prove that A has no inverse, and this matrix A is 1 0 2 0. So look at the solution. Since we have to show that A has no inverse, so similar to the previous theorem, we will assume that this statement is false. Okay, so what if this statement is false? We have to show that A has no inverse. So the correct statement is A has no inverse. So what is the negation of this statement? The negation of this statement is that A has inverse. So we contrarily assume that A has inverse. So on contrary, assume that A has inverse and suppose that this inverse is B and that B is A, B, C, D. What will happen then? Then if B is the inverse of A, then if I multiply A with B, I will end up with the identity. Put the values of A and B as well as identity. Here is A, here is B, here is identity. Now you have to multiply these two matrices and we will equate this with equal to identity. So if I multiply these two matrices, I will get this matrix. Now just compare to find the values of A and B. If I compare the first terms of each matrix, I will get A is equal to 1. If I compare the second term, I will get B is equal to 0. But if I compare the third term of the matrix, I will get 2A is 0. That means A is equal to 0. But this is the contradiction because previously I have found that A is 1, but here A is 0. These two things cannot be true at the same times. Either A is 1 or A is 0. So both things cannot happen at the same time. So this is the contradiction. Similarly, you can compare this also, but I'm not going to compare because I have already got the contradiction. So once I get the contradiction, that means everything is done. So this contradiction means my assumption was wrong. What was my contrary assumption? My contrary assumption was that A has inverse. So this contradiction tells me that this assumption is wrong. So if A has inverse, this statement is wrong. This means correct statement is that A has no inverse. Hence, I have proved that A has no inverse. And this is done.